talk about the problem of test pattern generation. Earlier we have already seen that given a circuit, gate level circuit is the example we talked about, we can define a fault model. Stuck-at fault model we have said is the most widely used fault model, and in all the examples we shall be showing now, we shall be considering this single stuck-at fault model. So, the title of the lecture is test pattern generation. So, let us see what is the scope of test pattern generation. So, we have a circuit, C, we have a list of faults F, we call it a fault list. Then we have a set of test vectors that we want to generate. This will be our output. Our input is the circuit and the list of faults. The objective of test pattern generation is to generate a set of test vectors to detect all the faults in F. Like for example, we took examples earlier. If I have a 3 input XOR gate, my fault list will see there are 4 lines. So, my fault list, the size of the fault list will be 8, there will be 8 faults, but my test set will consist of only 2 patterns 0 0 0 and 1 1 1. So, given my circuit, this should be my output. Okay. This is what we want to solve here. Okay. So, this motivation we have already taken some examples earlier, but let us again repeat this. Test generation can drastically reduce the number of required test vectors. Like in the example of an exclusive OR gate that you have taken, that any odd input XOR gate will require only 2 test vectors for testing all single stuck-at faults. You take an AND gate with 4 inputs and 1 output. Normally speaking, the number of input combinations are 16. So, for truth table verification you would be requiring 16 test patterns, but we have seen that only 5 test patterns are sufficient to detect all single stuck-at faults. So, there can be a drastic reduction in the number, right. So, these are some of the examples that I am showing here. For a 4 input AND gate, these are the 5 test vectors you need. For any odd input XOR gates, you need only 2 test vectors. So, from 16 you come to 5, from 32 you come to 2, that is a drastic reduction. So, let us take an example netlist with 3 gates. You see there are 2, 4, 5, 6, 7 lines. So, there are 14 single stuck-at faults. So, I am just showing, this is not the process how we are generating. Let us say the test vector 1 0 1 1. What are the faults it can detect? 1 0 1 1. 1 0 means here I get 1, here I get 1, here I get 1. So, you see a fault will be detected if the output G in the absence of fault exclusive OR the output in the presence of fault is 1, which means they differ. This is the necessary condition for detection of a fault. Now, 1 0 1 1, since the output G is 1, so obviously G stuck at 0 will be detected and EF are both 1. If either E is 0 or F is 0, then G will be 0, G will change. So, this fault will be there. Of course, E stuck at 0 is missing here, E stuck at 0 will also be there, E stuck at 0 will also be there. And similarly, here let us say either C or D. If either C or D becomes 0, then F will be 0, in turn G will also be 0, will change. So, C 0, D 0 will also be there. On the other side, if A is 0, output of this OR gate will become 0 and hence G will be 0. So, A 0 will also be there. So, like this, if you check, you will find that these test vectors are able to detect these faults, and you will find that these 5 test vectors are sufficient to detect all the 14 faults in this circuit. It includes all the 14 faults. Okay? Just an example to illustrate. So, this I suggest you verify all the other test patterns and check whether these faults are getting detected. Okay? Fine. Now, let us talk about some of the methods of generating test in a systematic way. Let us consider that I have a circuit which implements the function f equal to a b or b c. Here I am giving a method where I am showing a truth table. For the inputs a, b, c, these are the f, the output values a, b or b, c, a, b or b, c. Sorry, a, b or a, c, not b, c, a, b or a, c, a, b, a, c, yeah, a, c. Now, suppose we consider a fault on this line stuck at 0, we call it alpha. If this line is stuck at 0, that means this is always 0. So, effectively the function in the presence of fault will be only AC, because if this is 0, the term a b will disappear, this will become 0. So, the function f alpha in the presence of fault will be only a c. So, wherever a and c are 1, then only they will be 1. So, from the truth table, the idea is as follows. Let us just omit it. You look at all the rows and you find out the rows where f and f alpha are different. You see that they are differ here. So, 1 1 0 will be your required test vector. If we apply 1 1 0, then in the absence of fault output will be 1 and in the presence of the fault output will be 0. So, you can detect. Okay. So, this will be your required test vector. Well, but the problem here is that, well, you see, you have to start with the truth table, and constructing truth table for a large function is not easy. Suppose I tell you that I have a 30 variable function, 2 to the power 30 means how much? It is about 1 billion. Okay? So, it is huge. So, you really cannot construct a truth table of that size and compare the fault free and faulty output and see where they differ. So, this method, although it is good for understanding, this cannot be used for large functions. So, let us talk about a systematic method called the method of Boolean differences. This is an algebraic method, meaning that you have to carry out some algebraic calculation in order to find out what test vectors can detect a fault. Let us try to understand the basic principle behind the method first. Now, we define something called Boolean difference. Consider an n variable function f. F is a function of n variables x 1 to x n. So, when we define the Boolean difference, it is with respect to some variable x I, let us say x I. The idea is very simple. I have the function, I am talking about a variable x I. First I set x I equal to 0. Let us look at what the function is. I set x I equal to 1. Let us say what the function is. Then we take the exclusive OR of these two functions. That is what is defined as the Boolean difference. Let us see. Boolean difference notationally, this is expressed in the derivative notation df dxi. And as I had said, first in the function you set xi equal to 0, then in the function you set xi equal to 1 and take the XOR. The function with xi equal to 0, in short there is a notation fi 0. F suffix I 0 means the function with xi equal to 0 and fi 1 means the function with xi equal to 1. Okay. So, what does the Boolean difference really mean? You see, I am taking the exclusive OR of two functions. Now, when, let me just erase this. Now, when will the exclusive OR of two function be equal to 1? Okay. This will be 1 if either their values are 0 1 or 1 0, okay, which means this condition says that whenever xi changes, the function also changes. This is an indirect way of saying it. Boolean difference equal to 1 means when the variable xi changes, the output also changes, that condition. Okay? Fine. This is what Boolean difference means. Now, this is what I just now told. Boolean difference specifies the condition under which change in line xi will make the output change. We say will propagate to the output, the change will propagate. Now, talking about a fault on line xi stuck at C, C can be either 0 or 1. We are talking about either xi stuck at 0 or xi stuck at 1. So, to detect a fault, there are two things to be satisfied. Let us say, let us take a very simple example to illustrate what I am saying. Suppose this is my line xi and I am trying to detect a fault xi stuck at 0. To detect a fault xi stuck at 0, the first thing I have to satisfy is I have to apply a reverse logic value at the line where I am trying to detect the fault. Because if I apply a 0, then stuck at 0 also it will be 0 and 0 is also 0. So, I cannot see any change. So, first condition is the reverse logic value C bar must be applied to xi. We call here that we are exciting the fault. Then the change on this line I, there is a change we are forcing on this line I. Normally it will be 1, if there is a fault it will be 0. So, this change must be propagated to the output. How is the change we are expressing? We are expressing by the Boolean difference. So, these two things must be combined together. So, what we are saying that the two things combined together, we are saying that if we want to detect xi stuck at 0, we have to set xi to 1 first, which we denote by xi, and the change must be propagated to the output, which you are expressing by the Boolean difference. This and this must be 1, which means xi should be 1 and also Boolean difference should be 1. Similarly, for xi stuck at 1, I have to set xi equal to 0. So, that here I am writing xi bar. So, xi bar means xi has to be 0 and Boolean difference has to be 1. That means, I am exciting the fault and I am propagating the change to the output. Both the conditions must be true simultaneously. This is the basic idea behind the method of Boolean difference. Let us take an example. This is what I had said, excite the fault either xi bar and propagate the fault is the Boolean difference. Okay. Let us take a slightly complex circuit like this. Here there is a circuit with 5 gates. So, if you compute the function, realize you see function is this a plus b c bar and or c d. So, if you compute the Boolean difference, let us say we want to find out some faults on line C. So, we are computing df dc. First we are setting C equal to 0. If in this f you set C equal to 0, the second term will disappear and C bar will be 1. So, only a plus b. Then C equal to 1. C equal to 1 means C bar is 0, this will disappear, only D. So, XOR D. So, if you expand this, I am not showing the steps, the final expression will be this. Okay. So, when you are trying to detect C stuck at 0, the condition will be C and Boolean difference equal to 1. Boolean difference I have already calculated, C and this. So, it will be A C D bar, B C D bar, A bar B bar C bar D bar. From here directly you can know what are the test vectors will be in. See A C D bar means A is 1, there is no B. So, B is do not care, C is 1, D is 0. The second term there is no A. So, A is do not care, B C, D is 0. Here 0 0 1 1. Similarly, for C stuck at 1, you have a C bar here. So, the expression will be like this. So, A C bar D bar, A, B is not there, C bar D bar like this. So, you see the good thing is that for this faults you are getting all test vectors which can detect it. Do not care means it can be either 0 or 1. So, it can be 1 0 1 0 or 1 1 1 0 and this 0 1 1 1 and 1 1 1 0 I have already included and 0 0 0 1. So, there can be 2, 3, 4 possible test vectors here. Okay. Similarly, here. So, this is the method of Boolean difference, where with respect to the input, if you take the Boolean difference, then you can directly generate all the possible test vectors that can detect either stuck at 0 or stuck at 1 faults on those lines. Okay. This is an algebraic method, it generates all faults, but because it is algebraic, it is difficult to automate, it is difficult to write a program. Okay. So, practical test generation tools are normally not written using this Boolean difference method because of this problem. So, I am giving an idea what kind of methods are used there. There is something called path sensitization. I will just give you the basic idea behind this. So, you will have an idea. See, for testing we still follow the same principle as Boolean difference. We have to excite the fault, means reverse logic value we have to apply and propagate the fault effect to the output. The difference between Boolean difference is that for Boolean difference we started with the function expression and did algebraic manipulation. But in the method of path sensitization, we start with the gate level circuit and whatever we do, we work at the gate level circuit only. Okay? This is the difference. So, let us see what will happen. And another thing is that when you are talking about propagating, let us say, let us take an example. Suppose I have a gate here, the output is going to some other gate, let us say it is a NAND gate. This is the output and I am talking about a fault on this line, this is alpha. So, some change on this line must be propagated to the output. So, what we are saying is that whenever some gates are encountered in between, like it is a NAND gate, what should be the other input? Because if I apply a 0 on the other input, the output will be permanently 1, the change will not be propagated. So, I have to apply 1 on the other input. This is called non-controlling value. Similarly, for an AND gate also it will be 1. For an OR gate it should be 0. For a NOR gate it should also be 0. Okay? Then only the change will propagate. This is what we mean by non-controlling value. So, we will take an example, but the basic principle just works in two phases. So, what do you do? I will illustrate these steps with an example, do not worry. So, at the site of the fault, suppose we want to detect a fault. So, on the line where the fault is there, you assign a logic value that is reverse or complement of the polarity of the fault. Like in a line f, if you want to detect f stuck at 0, then you apply f equal to 1, the reverse value. Then forward drive phase, from this site of the fault, the line where the fault is there, you select a path to one of the outputs. You sensitize the path by assigning non-controlling values. We just now said what is non-controlling values. So, that change at the site of the fault will be propagating to the output. After we have done this, you will have to do a backward trace phase, because whatever logic values you have assigned, you have to backtrack, so that all the primary inputs are assigned appropriate values. So, once you have done that, you know what are the inputs that have to be applied. These steps, let me explain with the help of an example, then it will be clear. Take a circuit like this. There are 5 gates, and suppose we want to detect a fault on line E. This E is the output of this OR gate, E stuck at 1. So, in the first step what we said, that a reverse logic value must be applied at the site of the fault. So, because we are talking of E stuck at 1, what we do? We apply a 0 at the site of the fault, the reverse logic value, right. This is the first step. Then from the site of the fault, we have to select a path to the output. Here there is a one path only from this H to Z. So, next step we have to propagate the fault effect to the output. So, there is only one path, no option, and we have to apply non-controlling values. See, change on line E must propagate as a change on Z. For that, you see, I have an AND gate here, I have an OR gate here. I told for an AND gate non-controlling value is 1, for an OR gate non-controlling value is 0. So, what will happen is, you will apply a 1 here and you will apply a 0 here. So, if we do this, then it is guaranteed that any change on line E will be propagating as a change on line H and a change on line Z output, right. So, your forward drive phase is done. Now, you will have to do backward propagation. You see, backward propagation, what is the basic idea? That you have set this line E to 0, line F to 1 and G to 0. But what you have not done yet is that you do not know what values have to be applied to A, B, C, D. So, from E equal to 0 I have to propagate back, from F equal to 1 again I have to propagate back, and from G equal to 0 again I have to propagate back. This is called back propagation. I have to finally assign some values to A, B, C and D. Okay. Backtrace towards the primary inputs and assign values to the gate inputs. So, to make the output of this OR gate 0, both the inputs must be 0 0, A is 0, B 0, done. Now, F is 1, so this NOT gate should be 0, which means C is 0, and if C is 0, the value of G is automatically 0, you do not have to do anything more, it is already done. So, D can be do not care. So, you have got a test vector A 0, B 0, C 0, D do not care. You see, this is the basic idea behind the method of path sensitization. This is very simple in concept. You see, from the gate level netlist you can simply propagate forward and backward and generate a test. So, test vector will be this. But the thing is not so simple. You should remember something very clearly, that this path sensitization method is not as simple as this example shows, because during backtracking or backtracing there can be conflicts. Some path may tell that an input A must be set to 0, but some other path may tell that A must be set to 1, which will not work. So, you will have to go back, make some changes and again come back. Lot of backtracking may be required in such cases, okay? Or more than one paths may need to be sensitized together, but these are the things I am not discussing here, but you should remember this, because the practical tools are much more complex than what I have shown in the example. Very good automated test pattern generation, it is called ATPG, automated test pattern generation. Such ATPG tools exist, and sequential ATPG tools are more time consuming. We shall see later how sequential circuit test pattern generation can be handled. And as I said, we shall not be discussing fault simulation here in this course, but you should remember one thing, that the process of test generation, because of its complexity, is typically slower than fault simulation. So, with this we come to the end of this lecture. In the next lecture we shall be talking about some of the techniques that we can follow for generating test for sequential circuits, namely a generic strategy called design for testability. This we shall be discussing in the next lecture. Thank you.